So now let's discuss how we will do the post order traversal of our binary tree in an iterative manner. So just to remind you the logic of the post order traversal, we said that we do the post order traversal given a node. What we'll do is we'll check if our node is null. If it is null, then we'll simply return. Otherwise, what we should do, we should do the post order traversal of the left subtree. And after that, we should do the post order traversal of the right subtree. And after that, we should perform the node specific action, which might be just printing of the node value or anything that you want to do in your traversal. Okay, so that's our post order traversal. So if you look at the logic of generating the output, it says that of what I want in the output is the post order traversal of my left subtree. And then I want the right tree's post order traversal. And once I've done that, and then I want my node in the output. Okay, that's the logic. Okay, and for iterative post order traversal, what we are going to do is we are going to look at this output in the reverse manner. Okay, that's how we are going to look at it. So what I'm going to do is I'm going to have a stack around this output, and what I'm going to do is first I'm going to push node onto the stack, then I'm going to push the right subtree's post order traversal, and on the top of it I'm going to put this post order traversal of my left subtree. Okay, so that's the idea of doing it iteratively. Okay, so let's go and write the logic for our iterative post order traversal. So I have post iterative given a node. Okay, fine. So what will I do? I'll check if my node is empty, because if the tree is empty, there is nothing to do. So if my node is equal to null, in that case I should return. Fine. If that's not the case, then what I'll do is I'll have to create a stack similar to my pre-order traversal. Okay, so I'll say that let's have a stack S, and I'll create new stack of capacity which is equal to my pre-dot node count. So I got the node count of the tree in a property. Okay, so this is n node count. And once you do that, what would you do is you would go through your stack and pop out each node. So I'll have a looping construct while I'll say that check if my stack is empty, and it should be negative of that. Okay, so whenever if my stack is not empty, okay, then only do this thing. What should I do? Well, I should pop an entry from the stack. So I'm going to say that my current node is going to be s dot pop, and that's where now this thing comes in picture. Okay, so the moment I encounter a node, remember what we did in case of pre-order traversal. Okay, so in case of iterative pre-order traversal, whenever we encountered the node, we directly added it to the output. But now what we are going to do is we are going to add it to a stack. So this kind of stack which will store the node, above it the right subtree, and above that the left subtree. So now I'll need one more stack. Okay, let's call it the output stack, and I'll say that I'll create output stack, create new same tree dot node count. Okay, and I forgot one thing. To begin this loop, I need to have something in my stack. Okay, so I have to do s dot push my node. Okay, that is necessary. We forgot this thing. This was an important thing to do. So now what I have done is I have created an empty stack to store the states for my traversal, and one more empty stack to store this output in the reverse order. And now I pushed my root node onto the stack, and now I start my traversal. Whenever I encounter a node, I simply add it to my output stack. So I would say that output dot push current dot value. Okay, and then what I have to do is, on the top of it, what should come first? The right subtree and then the left. Okay, so what I will do is I'll do the reverse thing as compared to my iterative pre-order traversal. There I was first pushing the right and then pushing the left. Now I would do the reverse thing. Okay, so what I'll do is that I'll first check if current dot left is not equal to null. If that's the case, only then I would say that s dot push current dot left. So I'm going to push the left node first, and then I'll check if it has a right child. So if current dot right is not equal to null, in that case you should push current dot right. Okay, and then I'm comparing with the pre-order traversal. That's all that I need. Okay, so I'm done with my while loop, and I'm done with my post-order traversal. Okay, that's not the case. Yes, there is something left. Now we have output in the reverse order in our stack. So there is something that we need to do. What we need to do is we need to print the stack, right? So what I'll do is I'll ask question while my output stack is not empty. Is it empty? I'll do the negation of that. Okay, while my output stack is not empty, what will I do is, now here I will add the contents of my output stack to the output. So I would just say that print whatever is the result of output dot pop. So output dot pop operation, and my while loop finishes here, and then my post order iterative logic for post order traversal ends. Okay, so again, if you compare it against the recursive logic, what we are doing is when we encounter a node, first I have to do the left traversal and then the right traversal, but here it looks a bit different, right? Here it looks like the order is reversed, precisely because we are storing the output in a reverse order. So whenever we encounter the node, first thing we do is store the node in the output stack, then we store the right subtree's output, and then we store the left subtree's output. And now once they are stored in reverse order, we go and pop them from the stack. Okay, so that's the logic of iterative post order traversal. Again, if you think about the time complexity, all these operations are constant time, and now we can see that we are pushing a particular node to the stack S only once. So total number of push operations are going to be of the order of number of nodes in my tree. So let's say if my tree has n nodes, then I will have theta n push operations on my stack, and then I will have equal number of pop operations on my stack S. Similarly, I will have theta n push operations on my output stack, and then theta n pop operations from my output stack. And that's all that is there in this particular function. So the time complexity of this function is still theta n.